The year was 1969. It was a time of great social and political upheaval, but also a period of incredible technological advancement. The world was on the brink of witnessing something extraordinary, something that would forever change the course of human history. Across the globe, hundreds of millions held their breath. People from all walks of life, from different cultures and backgrounds, were united in their anticipation. They gathered around their television sets, in living rooms, in public squares, and in front of store windows, all eyes glued to the grainy black and white images being broadcast. They watched on grainy television screens as two American astronauts, Neil Armstrong and Buzz Aldrin, achieved what was once considered impossible, landing on the moon. This moment was not just a triumph for the United States, but a monumental achievement for all of humanity. It symbolized the boundless possibilities of human ingenuity and the relentless pursuit of knowledge. This incredible feat was made possible by a marvel of engineering, the Apollo Lunar Module, often referred to as the LM. The LM was a testament to the brilliance and dedication of the engineers and scientists who worked tirelessly to bring this vision to life. It was a complex machine, designed to operate in the harsh and unforgiving environment of space. This unassuming craft, with its insect-like legs and gold foil exterior, was the key to humanity's first steps on another celestial body. Its design was both functional and symbolic, representing the delicate balance between fragility and strength. The gold foil, for instance, was not just for show, it served a critical purpose in protecting the module from the extreme temperatures of space. A common misconception about the Apollo missions is the belief that the entire spacecraft that launched from Earth also landed on the moon. In reality, the journey to the moon was a highly coordinated and intricate process involving multiple stages and components, each with its own specific function. This is not the case. The Apollo spacecraft was a sophisticated assembly of different modules, each designed to perform a unique role in the mission. Understanding these components is crucial to appreciating the complexity and ingenuity of the Apollo program. The Apollo spacecraft consisted of three primary components: the command module, the service module, and the lunar module. Each of these modules was a marvel of engineering in its own right, meticulously designed to ensure the safety and success of the mission. The command module was the crew's home during the journey and housed the systems for return to Earth. It was a compact yet highly efficient space, equipped with all the necessary life support systems and navigation equipment. The command module was the only part of the spacecraft that would return to Earth, re-entering the atmosphere and splashing down in the ocean. The service module provided propulsion and support systems for the command module. It was the powerhouse of the spacecraft, containing the main engine, fuel, and other essential systems. The service module played a critical role in maneuvering the spacecraft and ensuring that it stayed on course. Only the lunar module, a specialized craft designed specifically for the lunar environment, actually landed on the moon. The LM was a two-stage vehicle, with a descent stage for landing and an ascent stage for returning to lunar orbit. This design allowed the astronauts to leave behind the heavier descent stage, making the ascent stage lighter and more efficient for the return trip. Understanding how the lunar module functioned is key to grasping the complexity and brilliance of the Apollo missions. The LM was equipped with state-of-the-art technology, including advanced navigation and control systems, which allowed the astronauts to land with pinpoint accuracy on the lunar surface. It was a two-stage spacecraft, with a descent stage for landing on the moon and an ascent stage for returning the astronauts to lunar orbit. The ascent stage was designed to be as lightweight as possible, with just enough fuel and resources to get the astronauts back to the command module. This ingenious design allowed for a lightweight and efficient vehicle, optimized for the unique challenges of lunar exploration. The engineers had to consider every detail, from the materials used to the layout of the controls, to ensure that the LM could perform its mission flawlessly. In the following sections, we'll delve deeper into the remarkable engineering of the lunar module, exploring its design, capabilities, and the role it played in making the Apollo missions an astounding success. We'll uncover the stories of the people behind the machine, the challenges they faced, and the innovative solutions they devised to overcome them. Join us as we journey through the history and legacy of one of humanity's greatest engineering achievements. The lunar module, nicknamed the Eagle during Apollo 11, was a study in contrasting design. It was a marvel of engineering, representing the pinnacle of human ingenuity and determination to explore beyond our home planet. Its two primary sections, the Descent Stage and the Ascent Stage, were almost like two separate spacecraft, each tailored for a specific purpose. The Descent Stage was built to handle the challenges of landing on the Moon, while the Ascent Stage was designed to bring the astronauts back to lunar orbit. The Descent Stage, as its name suggests, was responsible for the controlled descent from lunar orbit to the Moon's surface. This stage had to ensure a safe and precise landing, navigating the treacherous lunar terrain with utmost accuracy. It housed the descent engine, fuel tanks, landing gear, and a significant amount of equipment and supplies for the lunar surface operations. These components were meticulously designed to withstand the harsh conditions of space and the Moon's surface. This stage was essentially a sturdy platform designed to safely deliver the astronauts and their equipment to the Moon. It provided a stable base for the astronauts to conduct their historic missions, including the first steps on the lunar surface. In stark contrast, the Ascent Stage, perched atop the Descent Stage, was designed for a single, critical purpose: to lift the astronauts off the lunar surface and return them to lunar orbit. This stage had to be reliable and efficient, ensuring the astronauts' safe return to the command module. It was a much smaller and lighter structure compared to the Descent Stage. The Ascent Stage was streamlined to minimize weight, which was crucial for the limited fuel available for the return journey. This section housed the crew cabin, the ascent engine, and just enough fuel and resources for the return journey to the command module. The crew cabin was a compact space where the astronauts lived and worked during their time on the Moon. The two-stage design was crucial for mission success. By separating the functions of landing and ascent, the engineers could optimize each stage for its specific task, ensuring the highest chances of success. By jettisoning the Descent Stage after its purpose was served, the Ascent Stage was significantly lighter, requiring less fuel to escape the Moon's gravity. This clever design allowed the mission to be more efficient and increased the likelihood of a successful return. This ingenious design philosophy minimized the mass that needed to be launched from Earth, making the entire mission possible with the technology available at the time. The lunar module stands as a testament to human creativity and the relentless pursuit of exploration, forever marking our first steps on another world. The descent of the lunar module from lunar orbit to the Moon's surface was a complex and delicate maneuver. It required a blend of advanced technology, human skill, and precise calculations to ensure a safe landing on the lunar surface. It was not a simple freefall, rather it was a carefully calculated and controlled descent, requiring constant adjustments and precise navigation. The astronauts had to monitor their instruments closely, making real-time decisions to correct their path and ensure they stayed on course. The heart of the descent stage was the descent propulsion system. This system was designed to provide the necessary thrust to slow down the lunar module as it approached the Moon's surface, allowing for a controlled and safe landing. This system used a single, hypergolic engine that burned kerosene-50 fuel and nitrogen tetroxide as an oxidizer. Hypergolic propellants are unique because they ignite spontaneously upon contact, eliminating the need for an external ignition source. Unlike most rocket engines that require an ignition source, hypergolic propellants ignite on contact, providing a high degree of reliability, a crucial factor for the success of the mission. This reliability was essential, as any failure in the descent engine could have resulted in a catastrophic crash. The descent engine was throttleable, meaning the astronauts could adjust the amount of thrust generated, allowing for precise control over the descent rate and trajectory. This capability was vital for making fine adjustments during the final approach to the lunar surface. This level of control was essential for a safe landing on the lunar surface. The astronauts had to carefully manage their fuel and thrust to ensure they could land gently without running out of fuel or crashing. The descent profile involved several phases, including braking maneuvers, altitude adjustments, and a final approach phase where the astronauts visually selected a safe landing site. Each phase required careful planning and execution to ensure a successful landing. One of the most iconic moments of the descent was the 12:02 program alarm during the Apollo 11 landing. This alarm indicated that the lunar module's computer was overloaded with tasks, causing concern among the astronauts and mission control. This alarm, signaling an overload of the computer system, threatened to abort the mission. The astronauts had to quickly assess the situation and determine whether it was safe to continue the descent or if they needed to abort and return to orbit. However, thanks to the quick thinking of the astronauts and the support of mission control, the problem was identified as non-critical, and the landing proceeded, demonstrating the incredible skill and resilience of the team behind the Apollo missions. This moment highlighted the importance of teamwork, communication, and the ability to remain calm under pressure, ultimately leading to one of humanity's greatest achievements. With the lunar surface explored and samples gathered, the focus shifted to the next critical phase of the mission, returning to the orbiting command module. This was where the Ascent Stage of the Lunar Module came into play. The Ascent Stage, relatively compact and lightweight compared to its counterpart, housed the astronauts during their time on the lunar surface. It was designed to be their lifeboat back to lunar orbit. Its primary component was the Ascent engine, a smaller but equally vital engine compared to the Descent engine. Unlike the throttleable Descent engine, the Ascent engine had a fixed thrust output. This meant that once ignited, it would burn at full power, propelling the Ascent Stage off the moon in a single, continuous burn. Timing and trajectory were critical for this maneuver, as the Ascent Stage had to rendezvous with the command module orbiting above. A key feature of the Ascent Stage was its guidance system. This system, working in concert with the guidance systems on the command module and on Earth, allowed for precise navigation and maneuvering in lunar orbit. The Ascent Stage, after expending its fuel, would dock with the command module, allowing the astronauts to transfer back before the journey home began.